All right. Okay. All right. So the first section is about functions. A lot of stuff about functions, and functions are special relations, and relations are just a correspondence. Okay. So it's just a correspondence between two sets. Between two sets. Those sets that we'll deal with mostly in college algebra are the domain and the range. Does anybody remember what domain goes with in a problem? We're talking about a relation. So a relation, an example maybe is a set of ordered pairs. You know, there's an example of a relation. So the domain relates to which part of that? Does anybody remember from maybe they covered this in 7th grade math, I know, and they may have covered it before that, but we kind of touch base on it in almost every class. Domain goes with which part of an ordered pair? So what are the parts of an ordered pair? You got x and y. So these are x's, these are y's. Right? So the domain goes with which one, x or y? X, yeah. Domain, those are your x values. That means the range has to be your y values. Okay, so when we're talking about a relation, we're talking about functions, we're talking about that correspondence between the domain and the range, between the x and the y. And as we go through this course, one of the big things that we deal with is domain. And so that's a very important part. Another word for domain that I know I use it some in Algebra 1 is an input, and the range is an output. So I'm just kind of trying to put all those synonyms, all those words that mean the same thing there together for our relation, the correspondence between those two sets. The domain, x values, is the input. The range, the y values, that's the output. So no matter what kind of situation, if you see those words, you know, domain, you know, they're talking about the x values. Range, they're talking about the y values, the up and down. If they say input, they're talking about x. They say output, they're talking about y. So the terminology is a little bit different in college algebra than it is in Algebra 2. So a lot of the same things that mean the same thing, just they're using different terminology. So I want to try to kind of help with that. Okay, so a function is a special type of relation. Okay, a function from x into y is how we normally do functions. We take x values and we get y values from those. So we got maybe an equation, and we plug in the x's and get the y values to go with that. That's normally how we do a function. From x into y, what it does is it associates, correspondence associates, same word, each x with one y. Okay. Each x with one y. It doesn't repeat x values. Okay. One of the things that I tell my freshmen, they tend to understand this, is if you're going to function properly, you don't repeat your x's. Okay, so that's a good word of advice for life and functions in math too. Don't repeat x's if you're going to be a function. Okay, so functions don't repeat x values. It's okay if they repeat y values. That's not a problem. X values cannot be repeated if you're going to be a function. So let's start off by looking at a few relations and decide are they functions or not. And this will get us kind of some of the ways that relations are given to us. So we're going to answer this question. Is the relation a function? So example A, let's start with this relation. 2, 3, -3, 5, 6, 4, and 8, -2. So this relation is just a set of ordered pairs. I put it inside the curly braces there. That's means it's a set, but that means we're only looking at these. These are the only parts that are in this relation. It's the only ordered pairs that are there. So when we look at that, we want to say, okay, well, is that a function or not? So we look to see if any of the what repeat. X's, okay? So I got a 2, a -3, a 6, and an 8. No repeats. So is this a function? Yes. So yes. Yes or no on that's fine with me, okay? Example B, let's say we had another relation as a set of ordered pairs. Maybe we got -3, 7, 8, -1, -2, 7, and then 8, 0. Is that a function? Why not? That x repeats. We got an x value, that 8 repeating. That's the reason it's not a function. I'm just going to write out to the side, repeated x value, just so we know that's why. Now, it repeated the 7 as well, but does that make a difference? No. For just being a function, repeating y values is okay. Just can't repeat x values. Okay, so there's relations that are expressed as a set of ordered pairs. They can also show us a relation using what's called a mapping, where they have one bubble that's the domain and another bubble that's the range. And they just have some numbers in there, so that maybe they've got the numbers 3, 5, and 7. And then over here on the range bubble, they got -2 and 6. And what they have to do here, if it's a mapping, is they have to map the domain to the range using arrows. So they, maybe they draw an arrow from the 3 to the 6, from the 5 to the -2, and maybe the 7 goes to 6 as well. So it's just arrows that connect all those things. So we need to look at that and say, okay, well, is that a function? Yes. There's not 2 arrows coming from any x value or any domain value. So we know that this is a function, so yes. Okay. Example D, domain, range. Let's put some numbers in there. 3, -5, 8, 7, -9, 10. Is that a function? No, we got a domain value of 3, the x value of a 3. It's in the domain bubble. It's an x value. It's going twice. It's going to the 7 and then to the 10. So it's counted twice. So that's a repeated x value. So that's a no on that. Repeated x. Okay. Not too bad. Pretty easy. All right. Let's look at maybe this way of expressing a relation. Y equals 3x minus 2. Oh. That's an equation. That's not a set of ordered pairs, but it is. Hey, it's a set of ordered pairs because you got x over here and you multiply x by 3 and then subtract 2 and you get a y value that goes with that. So it is a set of ordered pairs. It's not expressed as a set or a mapping. It's expressed as an equation, but we can take any equation and create a graph with it, right? We know how to graph y equals 3x minus 2, hopefully. So I'm just going to sketch that graph. We don't have to have it be too accurate. So I'm just, draw myself a little coordinate plane. How do I graph that? What's my first thing to do? Yeah, 3x will be over 1. Alright, so yeah, I'm going to put some tick marks here. Yeah, my y-intercept, what that's called, -2. And then my slope is 3 over 1, so I can go up 3, 1, 2, 3 over 1, get a point. And I just get this line that does that. Okay, and when I look at that line, you know, that line represents all the ordered pairs that come from that equation. And one of the tests that you've heard of before to decide if something is a function or not when you got a graph. Does anybody remember what that is? Three words. And then the last word is test. I'll give you that one. Going back, I don't even remember it now. Something line test. First the V. Vertical. The vertical line test is how that's going, you can test that to see if it's a function. And with the vertical line test, what you're doing is you're taking a vertical line and you're placing it all over the graph to try to find a spot where that vertical line hits it twice. If it hits it twice, that means an x value repeated. And then that means, well, it's not a function. So if I try to lay a vertical line on there, I'll draw some on here. There's vertical lines all over the place. Every one of those is only hitting that red line in one spot. So this one passes the vertical line test. So it is a function. So passes the vertical line test. That's how we know it's a function, okay? We've graphed it and looked at that. If you've already got your graphing calculator, you could graph that by hitting y equals and then just put in 3x minus 2 and telling it to graph it. We'll get that same line that I just drew there. And you could do the vertical line test on that graph your calculator's drawn. Okay, so don't shy away from using a calculator to give you a quick graph to decide if something's a function or not. Okay, let's go to one that's a little bit more difficult. Let's say we had y squared is equal to x squared minus 4. Huh. That's strange. It's got a y squared. Say it again, like what was that? Okay, what would that let us do? Taking a square root. Well, that would be factoring. That's a difference in square roots. I mean, we're not trying to solve this. We're looking to decide if it's a function or not. Solving it's a whole different game. This is you guys are replacing y with 0 and trying to solve it. That's not what we're trying to do. We're trying to figure out, is this a function or not? You said take square roots. That's a good idea. You may not have known it was a great idea or not, but it is. If I take the square root of each side, that's going to give me plain y over there, and that's a little bit more familiar. I'm used to plain y, not y squared. I'm not really used to that at all. But I'm used to plain y. But when I take the square root of the other side, it's got a plus or minus in front of it. Okay? And when I look at the graph of that, I can use my graphing calculator to help me graph it, and I've got a positive side and a negative side I have to graph. So that's where knowing that plus or minus has to be there is pretty important. So anytime you introduce a square root into a problem, you have to put a plus or minus in it. If the square root was already in the problem, no problems. If you put a square root in a problem, plus or minus every time. It has to be plus or minus. Okay, so I'm going to do the positive side, so I'm going to get second square root. And then I'm just going to type that in, x squared minus 4. And then I'm going to go to y2, and I'm going to get the second half of that, the negative side So negative square root x squared minus 4. And I'm going to graph both of those at the same time. So there's the blue one, that's the positive side. Here comes the negative side. Does that pass the vertical line test? If I can take a vertical line right here. It hits it twice, doesn't it? Does that pass or fail? Fails. That fails the vertical line test because I put a vertical line somewhere on there and it hit the graph twice. Okay, so this one's a little bit more difficult. Maybe it's a problem you haven't seen much of because you got y squared. We don't deal with that a whole lot, but we can get it down to just plain y, and then we kind of know what we're doing a little bit more out of that. So that is not a function. And it fails the vertical line test. Is the reason that that's not a function. Okay? So not too bad. All right. Now, deciding if something is a function or not is what lets us get into function notation. And this is something you've seen for a while. Function notation, f of x equals, and we'll just take an equation, 3x plus 5. Just some equation. I know that's a function because y equals 3x plus 5 is a lot like that y equals 3x minus 2 that we did earlier. That would pass the vertical line test. If it passes the vertical line test, I know it's a function. So I know that 3x plus 5 creates y values, and it doesn't repeat x values. So I know that's a function. Function notation, this f of x, remember that's the same thing as a y value, but it's just a little bit more descriptive. It tells us this y value comes from this x value. So it's that mapping, that pairing of the correspondence between the x's and the y values. And what letter are we on here? G. We'll let this be example G. We want to find a function value. Let's find f of negative 5. So finding f of negative 5 just means, well, that 5 goes in the place of x. That negative 5 does. So we're plugging that in and working it out. The left side is just the notation. Okay? It's just the f of negative 5. That just means the y value when x is negative 5. That's all that means. It's not f times negative 5. That's a very common mistake that happens a whole lot. So on the right side, you're just working that out. 3 times negative 5, negative 15, plus 5, negative 10. So f of negative 5 is negative 10. That's what we found as an answer. The ordered pair that comes with, negative 5, negative 10. That's the ordered pair. The x value is negative 5, the y value is negative 10. That's what we're finding with that function value out of that. Not much in the way of difficult on that part. Okay. Scroll up so you can still see that one. Let's take this function. F of x is equal to 2x squared minus 3x. And we want to find the function value of f of 2x. So we're going to find f of 2x. What's that mean we put in the place of x? 2x. So 2 parentheses 2x squared minus 3 times 2x. Okay? Now, we have to look at that and say, okay, I got to follow order of operations. So what has to happen first? Parentheses, and then from there, then multiplication, division left to right, and then addition, subtraction. So what happens in this problem first? What's the first thing I do? I would square that 2x, right? Because it's got an exponent. 2x times 2x would be 4x squared. So technically that's the order. I'm not done anything else yet. I'm just doing that first step. I would think most of you could do more than one step at a time, and I'm absolutely encourage that. And then from there, we took care of the exponents. Now we just need to do our multiplication division. So 2 times 4x squared would be 8x squared, and then we have minus 6x. And there's our function value for f of 2x. Not a number, but yet another equation out of that. So very basic stuff, but still important. Let's find if f of x is equal to 2x squared minus 3x still. Let's find f of negative x. Let's find f of negative x. This is one of those things where you got to be careful. And ACT likes to do this a lot. They like to throw a negative in there because nothing really interesting happens with a positive number. Lots of interesting things happen with negative numbers. So when I do that, plug it in. And what happens when you square negative x? It becomes positive 1x or 1x squared or 1x to the third or what? It can't turn into just a 1 because it's an x. It'd be x squared, right? So it just turns into 2 times x squared, which is just 2x squared. And then we have negative 3 times a negative x, which would give us, positive 3x. And then there's our function value for f of negative x. You can't simplify that. They're not like terms. One of them's x squared, one of them's just plain x. You got to be careful about that sort of thing. Okay. So let's say we had a function, f of x is equal to, let's just use that same one. It seems to have some interesting things happening to it. And they want us to find negative f of x. What in the world? Negative f of x. So, what does that mean? To do to 2x squared minus 3x. Say that again. Is it divided by negative 1? Does that show division out here? It ends up giving you the same answer, but you're not trying to solve for f of x. You're trying to just do this operation. So when they put a negative in there in front, that's understood to be what in front of f of x? A negative. It's like a negative 1 is there. So what that's telling me to do is take negative 1 and multiply it times that function. We're not trying to get f of x by itself at all here. We're trying to work out what's this say to do. It says take negative 1 times f of x. Well, f of x is this whole thing here. So I'm going to multiply negative 1 times that whole thing, which just distributes a negative 1 to it. And get negative 2x squared plus 3x. And that's what negative f of x is equal to. Don't fall into the trap of trying to get f of x by itself. It's not going to happen. That's not what you're doing. You're trying to do the operation that they're telling us to do. Okay. So a similar example of that would be, f of x. Let's use that same one, 2x squared minus 3x. And they say 3 f of x. We'll find 3 f of x. What's that mean we do to the problem? Multiply it by 3. Just take that it really is that simple what they're trying to get you to do. The notation is where we got to get to, which is a little bit different than what you may have seen in Algebra 2. I'm not sure. I didn't teach it last year, so I know y'all had Coach Mac, so I'm sure y'all enjoyed that. So hopefully you'll enjoy my class just as much. So 6x squared minus 6x. Not 6x squared, 9x. 6x squared and 9x. Just good old distributed property there. Okay. This section is really good about getting us some algebra practice here. Let's say that we have f of x is equal to 2x squared minus 3x. I'm using that same one because it's got a lot of interesting things happening to it. And they want us to find f of x plus 2. So maybe now they are telling us to put something in the place of x on this one. So it's not just multiply the whole thing by something. It's put something in the place of x. So f of x plus 2 means we put what in the place of x? Okay, so and we can't leave that alone. We have to simplify it if at all possible. So that would mean we would need to work out any kind of algebra that happens there. So the algebra that happens here is what? What happens first? My exponents. So I've got an exponent right here on the x plus 2. It's squared. What happens when you square x plus 2? No. Close. Wrong. Very common wrong answer for that. What's it mean to square something? Multiply it by itself. So if I multiply, maybe over here on scratch paper I say x plus 2 squared means x plus 2 times x plus 2. No. That's the same wrong answer. If I multiply that out, wrong again. X times x, x squared, plus 2x, plus another 2x, then plus the 4. So it turns into x squared plus 4x plus 4. Okay? So now we have 2 parentheses, x squared plus 4x plus 4. And then I'm going to go ahead and do the distributed property with a negative 3 because that's what I would normally do if I was working this problem. Minus 3x minus 6. And then the next step would be distributing that 2. That's 2x squared plus 8x plus 8 minus 3x minus 6. And now what do I put together? Like terms. So I'm putting the like terms together for that. So 2x squared doesn't have anything like m. But I got an 8x and a minus 3x, so that'd be 5x. And then I have 8 and a negative 6, that'd be 2. And there's my f of x plus 2. Got to remember some. That's a very common mistake that happens a lot in every math class that I've ever taught. That happened, getting that x plus 2 squared and putting x squared plus 4. So don't feel bad about that. That just happens. So, but we know better than that now. So I'll scroll back up so we can still see that. Let's do this one. Example M. And let's say we had f of x. And let's just use that same one again. It seems to have a lot of interesting things happening. We want to find f of 2x minus 3. A little bit more complicated style of problem there. because you got a 2x minus 3 that we're plugging in for x, which is a little bit more difficult than x plus 2 was. But the same kind of problem. 2 parentheses 2x minus 3 squared minus 3 times 2x minus 3. You know, I'd go somewhere over on the side and say, well, 2x minus 3 times 2x minus 3 be 4x squared minus 12x plus 9. And then I might go ahead and multiply that times 2. 2 times 4x is 8x squared. 2 times 12, negative 24x. 2 times 9 is 18. Minus 6x plus 9. Well, that's just going ahead and multiplying that out. All in one step there. If you remember from Algebra 1, we talk about, or when I teach Algebra 1, I talk about the shortcut of squaring a binomial, that you can square the first piece, that's a 4x squared, square the back piece, that's the back end, and then you multiply them together and then double it, gets you the middle piece. So that's a shortcut to do that. You square the first piece, gets 4x squared. Square negative 3, get a plus 9. 2 times negative 3 is negative 6, and double it, that gets you the middle. Anytime you're squaring a binomial, that's the shortcut that you can use to do that. Just speed things, you know, as we get a little further, you know, speed is kind of helpful. So let's put the like terms together. So we got 8x squared, negative 24, negative 6, negative 30x, and then 18 and 9, 27. And there is our f of 2x minus 3. Not too bad. Easy thing. Okay. All right, let's look at maybe using our graphing calculator to evaluate some number stuff. Okay, so this is an easy gig here. So with the TI-84 plus whatever version you got of that. So what are we on? N. Example N. Let's say our function is this. F of x is equal to 3x squared minus 5x plus 7. And they want us to find f of 1.25. Okay. So with the graphing calculator, you could do that by hand. You know, just plug that in. You know that what you're doing for that. You'd plug in 1.25 for x and work that out. You could do that by hand. I'm going to show you a quick, easy, get an answer with your graphing calculator. For when it's just numbers, it really can speed things up. Sometimes that's what you need on the ACT. You just need a number out of that thing. You know, what's the y value that goes with this x value? So I'm going to go to y equals. Is how I tend to do this. And then I'm going to clear out these guys. And I'm going to type in that function, 3x squared, 3, the x there by alpha squared, and then minus 5x, and then plus 7. Okay. And I can hit graph, you know, just gets me there, and it'll show me what that looks like. We should know that that looks like a parabola. It opens upward, has a vertex in the first quadrant. A lot of things we know about those. We're going to have a whole chapter about quadratics and stuff that we'll do. But we see that that's the graph of that. But we don't need the graph. We need the number that happens when x is 1.25. And one of the ways that you can do that is with the trace button on your calculator. So you can hit trace and then type in 1.25. And down there at the bottom, it gives you the y value that goes with that in a decimal form, which is absolutely fine that we get that because we started with a decimal, so we wanted decimal form of that. So 5.4375, and we'll just use all of them because it's not that long. 5.4375. That's one way to get it with the calculator. If you were going to have to do like several of them at once, you could use the table on your graphing calculator to do that. You may have done this in Algebra 2, where you go to second and then hit graph. and you got this table, I've already got some x values that I've typed in, and it found me the y values. So if I were going to do 1.25 here, I just type it in 1.25, hit enter. If I needed, you know, what's that? The y value in x is 17. You know, I can type that in, get 789. That it just cranks it out. If your graphing calculator won't let you type numbers in there, is anybody's not letting them type numbers in there that's got it? Okay, I'm going to show you how to set it to where it will. Okay, so what you want to press is second window. Second and the window button. And that will get you to this table setup menu. So second and then window is up there right beside the y equals button. Okay, you want yours to look like this. It doesn't matter what these numbers are, but you want your independent to be ask and your dependent to be auto. Independent ask is the x value, x is the independent variable, y is the dependent variable, and it'll automatically calculate that. So you want your independent to ask and your dependent to auto. If you've got it set to that, then when you go back to your table, you should be able to type in your values. And you know, you just type over, if there's something already in there, you can just type over it. You know, get that number out of that. You just type over the top of it, and it'll delete it and do the new one. Okay. And you can type in as many as you want there, and go from there. So like, if I just wanted to know, you know, I needed to know, find f of 26.07. 26.07. That's a weird number. It's not something I could quickly do in my head. I could type that equation into my calculator, go to y equals, and do and go to the table and do 26.07. 1915.6. 1915.6. If I were in my in the graph view of that, I could hit trace 26.07 and see what happens. It won't let me do it there. So this is where the table does better. The reason it let us do 1.25 and wouldn't let us do 26.07 is because when you're in the graph window, it only does the values that are seen on the graph. 26.07 is way off. When you look at that graph, when you look at that graph, it goes to 10 here. 26.07 is way off the screen. So it won't let you do a trace on a value that's off the screen. So that's where the table is a little better option, because it doesn't care what the graph's got. It just works it out in the equation. So it's a little bit different programming format there. So if you're looking for something close to the origin, a trace may be the quicker way to get there. If you're doing just random numbers, then the table is probably the best bet on getting it to crank out a y value for an x value that you're given. But real easy stuff there. Okay. All right. So that gets us through the mainly review part of section 1. So let's get into the part where we got to learn a little bit of notation. Not a hard part, but the notation's a little bit different for you. Okay. So we're going to talk about the domain of a function. And one of the things you'll realize with college algebra is that the lessons, each section has kind of got a little bit more material than maybe one section in algebra in your high school math classes had in it. So thus we teach one day and you work the next kind of idea out of that. So if we're talking about domain of a function, what are we talking about? The x's that work for that function. That's what we're talking about. The x values that work for a function. Okay, the x values that work for a function. Now, with domain, normally domain starts with all real numbers. all real numbers is from negative infinity all the way up to positive infinity. Okay? The notation that we've got to learn is called interval notation. Anybody do that in Algebra 2 last year? Did y'all do interval notation with parentheses and brackets? That tells me no, okay? Which is fine, because it's more of a college level, notation, okay? So we're going to learn it. All real numbers means every x that there could be. The interval notation that goes with all real numbers is negative infinity to positive infinity. And we know what the infinity sign looks like. Probably know someone who has that as a tattoo. Okay? It's kind of trendy right now. Okay? So the negative infinity to positive infinity is the interval notation for all real numbers. Now, the parentheses in interval notation means you're not counting that number. And if we use an infinity symbol, we have to put a parenthesis because we could never get there. Like once I think I've got to infinity, so all somebody's got to do is say +1, and they win. You can go further. So you could never get to infinity, or as Buzz Lightyear says, or beyond. You can't go beyond infinity. You're always just going to be approaching infinity. So parentheses will always occur with the infinity symbols. Domain for functions has a few red flags that we look for, and there's only a few. There's only these red flags. One of the red flags that we look at is x's in the denominator. If there are x's in the denominator, then that means there's restrictions on the domain, and we've got to find them. Okay? So we're looking at that red flag that tells us we got to change our domain is that there are x's in the denominator. Another red flag is square roots. Okay. Now, the red flag where x's are in the denominator, the reason it's a red flag is what number can we never divide by? 0. That's the only number we can never divide by. Okay? So, that's the problem. In square roots, what kind of numbers made something weird happen? Negatives. That got us into the the imaginary numbers, complex numbers. Okay? So with square roots, there's a restriction on the domain that says that we can only deal with positive square roots. Okay? So what we're gonna do is we're gonna look at some functions, and we're gonna tell what the domain is, and then we have to look for these red flags. We have to look for, okay, well, is there x's in the denominator? Are there square roots in the problem? Okay, if there are, then I'm going to show you what to do. Okay, and it's going to be related to with the x's in the denominator, division by 0. What would make that happen? And then what would give us only positive numbers in the square roots? So we're going to look at those. Really, those are the only two red flags you really have to look for when you're trying to decide what the domain of a function is. If it doesn't have either of those things happening, then it's all real numbers, negative infinity to positive infinity. Those are the red flags we're looking for. Domain red flags. That's what we want to find today. Okay, so let's look at an example here. I don't know what letter we're on. O. The donut example. Say we have a function, f of x is x squared plus 5x minus 7. Okay. If I'm looking at that and I want to find the domain. Find the domain. Okay? If this is our function. Does it have a red flag? It does? Where? Do I have x in the denominator? In that problem? No, there's no x in the denominator. There's not even any fractions in it. So there can't be an x in the denominator. So that red flag doesn't exist. Are there any square roots? I don't see a square root. I see a squared. That's not a square root. That's a squared. I see a plain x. That's not under a square root. That's plain x. I see a 7. It didn't even have an x. There are no square roots. There are no x's in the denominator. So that means there are no red flags for this particular problem. So the domain is from negative infinity to positive infinity. And maybe you're over the side, you're saying no red flags. No red flags on that one. Because it didn't have x's in the denominator and it didn't have any square roots. Okay? Let's look at this one. Let's call it g of x, just to give it a different name. Tired of f of x. Let's say we had 5x over x plus 3. So we look at that function. They're telling us it's a function because they put it in function notation. Okay? And so we don't have to test to see if it's a function. But we want to talk about the domain of that function. So let's look to see if it has any red flags. Does this one have red flags? Which one? Yeah, x is in the denominator. And the reason that that's a red flag is we can't divide by 0. So what we've got to look at is say, okay, what would make this a 0? So to make that a 0, we can set the denominator that has an x in it, set it equal to 0 and solve it. So I'm gonna, we got a red flag right there. That's what we're thinking. In your mind, you pop up a red flag when you see that x in the denominator. So I'm going to set that equal to 0 and solve it. Subtract 3. X equals negative 3. If x was negative 3, negative 3 plus 3 is 0, and I would end up with division by 0. So that's the number that screws things up. He's that guy, as they say. Okay, don't be that guy. That's the guy. So that means negative 3 is not in our domain. Have any other numbers but negative 3. We can't have negative 3. Okay? So, negative 3 is excluded. So I'm writing out what I'm thinking from the domain. So here's how we got to write our answer. We're going to go with, we're going to use the form that you're probably familiar with first. This is set notation, or set builder is what it used to be called. And it's x, straight up and down bar, x does not equal negative 3. Anybody seen that before? No? Oh dear. So that just means it's all x's, but x can't be negative 3. That's what that says. Okay? In interval notation, and this is one of the things that you've got to really work at learning, is interval notation. Interval notation, we're going to go from negative infinity. So remember, we always start with that being our original domain. Well, this one starts at negative infinity, and then it's traveling along the number line. Everything's going great. And then there's that problem number, the negative 3 coming up. So I've got to jump over again. Okay? In interval notation, to jump over that negative 3, you put a comma, negative 3, and then we're not including negative 3. Negative 3 is not part of our answers. And bracket would say it includes it. We want to not include it. Parentheses. Remember, that's the thing you got to remember. I will put a star up here. Parentheses, not included. Bracket, included. All right, so parenthesis on that. But we're just jumping over the 3, or the negative 3, and then we're going to start again and go toward positive infinity. So this is where we use what's called a union. So it's just a U shape there. It's not the capital U like you would do like that. You just leave off the little tail part. Union, that means we're going to pick up again. Okay, we're going to start at -3, not included. And there are no other problem numbers, so we're just going to truck along all the way to positive infinity. And that would be our interval notation for that. Okay? So we go to negative infinity, we're skipping -3, so that's where this -3 is. The interval notation, it looks like ordered pairs, but it's not. It's x values only. When we're talking about domain, we're talking about x values. So these are intervals of x's, is what we're dealing with here, not ordered pairs. Okay. We're going to use interval notation the whole class, so you'll get better at it. It may seem like, wow, this is out there. You'll get better at it as we go, I promise. Example Q. Let's say we had, I'm going to use h of x this time, 12 over x squared minus 16. The function, does it have red flags? Yes. What? X is in the denominator. Good job. Okay? So we got an x in the denominator, so that tells us we got a problem. We need to figure out what numbers would make that denominator 0. So we're setting x squared minus 16 equals 0. Say it again, Hunter. Yeah, x plus 4, x minus 4. So he's factoring that as a difference of squares, is what that is. And then what do you do with each of those factors? Set them equal to 0. So real easy math there. So x can be -4, x can't be +4. Those are the things x cannot be. In set notation, it's easier. I mean, no doubt. That's easy to write. That's the set notation of that. X can't, you just basically, these are the conditions of the thing. In interval notation, you got to hop over the -4 and then hop over the +4. But you got all the numbers that are between those two. So, interval. We start at -infinity because all those numbers work. -5, -6, on down to -infinity. All those numbers work. And then the first number that we come across on the number line, when we're traveling on the number line, maybe maybe that helps with the interval notation. I think it visually helps me. Down here is -infinity. I've got to skip over -4. I got that -4 is I'm jumping over him. So I'm going to travel, I'm walking along the number line here, and then I get to -4 and I got to skip him. So I got to report that I'm skipping -4 on my interval notation. So that's going to be -4 right there. And I'm skipping it, so what do I put? Parentheses or bracket? Parentheses. Okay? And then I'm going to pick up and I'm going to start walking this way. So I got to have a union. And right after I hop over -4, well, there's -3.9999999, that I've got there. So I'm just right after -4. So I'm going to use a parentheses and then a -4 there to start walking again. Well, I'm going to walk till I get to what number? +4. I'm skipping it. I'm going to jump over +4. So what's the next thing I write in my interval notation? A 4. Yeah, the next number I get to that has something happening at it. So I'm going to put a 4 there. Let me change back to the blue. Okay, but is that the end of the thing? No, I got all the numbers after 4 that work. So there's another U. And then how do I get all the numbers after 4? 4 to positive infinity. And if you want to put a plus in front of the infinity to say it's positive infinity, you can. I don't. Your book doesn't. But I'm not going to count off if you do that. But that's our interval notation. So maybe the number line might help a little bit as far as visually thinking about what numbers do I need to hop over, what numbers do I need to not hop over. Okay? Not too bad. You guys solved that quadratic really easily. That's promising. Very good. Very good. Example R. E. Square root with a 2x minus 6 on the inside. Is there a red flag? Yeah, there's a square root with a letter inside of it. It's also got a 2x and a minus, it's got 2x and then minus 6 also inside of that. So there's the red flag, is that square root there. So that's going to tell me I can only deal with what kinds of numbers. Well, what numbers can we take the square root of and not get an imaginary number? Positive and what other number? Say it again. 0. You can take square root of 0, right? 0. Square root of 0 is what? 0. So that's included. 0 is one of those included numbers. So these, all you got to do is take whatever's underneath the square root and set it greater than or equal to 0 and solve it. If I set that greater than or equal to 0, I'm going to get the 0. Then I'm going to get all the positive numbers, because all the positive numbers are greater than 0, right? So that's the logic behind that. If I set that greater than or equal to 0, I'll get 0 and only positive answers as my domain. So for that, you're just going to solve it. Good old Algebra 1. And then we would divide by 2. And I don't flip my symbol because I didn't divide by a negative. So it's x is greater than or equal to 3. So with our set notation for that, this one, it's the same idea. You're going to curly brace, x, straight up and down bar. That means x such that, and then we just write that inequality. X is greater than or equal to 3. That's our set notation. That tells me that the x values at work are 3 and everything above it. Okay? With our interval notation, and I do both forms here. Your book tends to do both forms some as well. It kind of bounces back and forth. Interval is what we will eventually just only do, just because it's more collegiate. It really does work well. And then, so I want x values that start at 3 and go up. So interval notation, I'm going to start at 3. So if I think about a number line, down here's negative infinity, up here's positive infinity. 3 is somewhere there. It's got an equal to mark, so does that mean 3 is included or not? Yes, it is included. Okay? So I know I'm going to start at 3. And I'm going to go which direction? Toward positive infinity. Yeah, I'm going to go to the positive side because it's greater than that. So that's the interval that I need to write. So if I start at 3, including it, and go to positive infinity, I know I got a 3 here. What goes beside it? Positive infinity. The notation, positive infinity is going to have a parenthesis. What should go here? Parenthesis or bracket? Why bracket? Because it's included. That equal to mark there tells me that bracket has to be there. So there's my interval notation. Okay? Don't shy away from drawing a number line. If it helps you get that interval notation, then do it. Okay? Because I think we all know how to graph that inequality. We can all graph that. The interval notation is the new thing. Okay? Let's do this one. Well, there we go. S. F of x is equal to 7x minus 3x squared. Any red flags on this one? No, there's no square roots. There's no x in the denominator. So that means our domain in set notation, we didn't do that on the first example. You can just do that. X such that it's all real numbers. What's the interval notation for all real numbers? Good job. Negative infinity to positive infinity. Always parentheses on the infinities. Super easy stuff there. No red flags, that's what your domain's going to be. So those, sometimes I do a lot of examples of the red flag problems, and we don't do very many of the no red flag problems. So I wanted to throw another one of those in there. Okay? Let's do this one. G of x is equal to the square root of 8 minus 2x. And then that's all that's under the square root. We'll go ahead and put a plus 7 out there on the side. Not that it matters. So, is that a red flag? Yeah, absolutely. We see that square root, that should automatically think, okay, there's a red flag. Got to do something about that. So how do I find out what x values I can use? Not equal to 0, but greater than or equal to 0. So the inequality part is with their square roots. Okay? So we want that answer that's under the square root to be 0 and positive numbers only. So that's why we set it greater than or equal to 0. Then solve it. Minus 8, so negative 2x greater than or equal to negative 8. Okay, so yeah, you got to flip the symbol. X is less than or equal to positive 4. So our set notation is just curly braces x such that x is less than or equal to 4. Our interval notation. We're looking at all the numbers that are less than 4. All the numbers that are less than 4. Okay, so if you say negative infinity, I got to put a parenthesis there. 4 with a bracket. Good job. Good job. Absolutely. And there's your interval notation. Don't get any numbers above that because it's all the x values that are less than or equal to 4. Okay. And again, don't shy away. If you need to draw that number line for this inequality, the graph of that, you get it, Trevor? It doesn't matter because it's just a plain 7 that's not underneath the square root. So the only part that matters is the part under the square root. It's kind of like up here on this example there was a 12 up there. It didn't matter because it wasn't an issue because it didn't have an x and it wasn't in the denominator. That great question though. Great question. Okay. Let's do a fun one. I love this one. Example U. Let's do k of x is equal to the square root of 2x plus 10. All that divided by x minus 7. Okay. There's a lot going on there. Is there red flags? How many of them? 2 of them. So there's 2 things we got to do here. So we got a double red flag. There's a red flag for the square root. There's a red flag for the x minus 7 in the denominator. So you just got to do both of them and take care of it. Okay. So I'm going to set them up. How do I set up for the x in the denominator? Since that's the first one we talked about. Yeah, x minus 7, set it equal to 0. And then What do we do for the 2x plus 10? Yeah, put it greater than or equal to 0. And then you're just going to solve both of those. So x can't be 7. Minus 10 minus 10, 2x is greater than or equal to negative 10. X is greater than or equal to negative 5. Okay, so our set notation for that just means we need to report both of those things. X such that x is greater than or equal to negative 5, and then x does not equal 7. Set notation is absolutely easier than interval notation, no doubt. Okay. The interval, more difficult. This one's pretty complicated because you got two things going on. Okay. Let's look at what's going on here. It says x can't be 7. So that's over, on the positive side of 0. And this says that x is greater than or equal to negative 5. So that's on the, it's starting out on the negative side of 0. Okay? So it's greater than or equal to negative 5. So what's our first number we'll start with? Negative 5. So my interval notation will be bracket, negative 5. And then I'm walking along, everything's going great until I get to what number? 7. It's the one that x can't be. So I got to jump over 7. So how do I jump over 7 with interval notation? So 7 is the number, parenthesis, and then I got to start after 7. U, parenthesis, 7 to infinity. Good job, guys. You got it. You got it. Okay. Not bad at all. Not bad at all. Okay. Questions about interval notation? You guys have got, getting the hang of it. It's going to take some practice. That's what we'll have tomorrow for. But you're getting the hang of it. Okay. All right.